What if I told you that the very ground beneath our feet was once a molten chaos, slowly shaping itself into the first landmass that would host life? Imagine witnessing Earth's first continent emerging from fire and fury. Hello everyone. Welcome back to our channel, your unique gateway to knowledge and understanding. If you haven't yet liked, subscribed, or shared, make sure you do. Comment below and tell us where you are watching from. The story of our planet begins not with life, but with land, the first stable ground that rose from the chaotic, molten surface of early Earth. To truly understand the first continent, we must go back more than 4 billion years, to a time when Earth was barely recognizable. Imagine a world of blazing heat, constant volcanic eruptions, and a sky filled with thick clouds of vapor and ash. There were no oceans, no trees, no animals, only fire, stone, and raw energy. Amidst this relentless turmoil, small islands of stability began to emerge, the very first fragments of continental crust. These early proto-continents were forged by the extraordinary forces of the planet itself. The Earth's interior was hotter than it is today, with immense heat generating pressure that pushed molten rock to the surface. Volcanoes erupted endlessly, spewing magma, minerals, and gases, gradually building layers of rock. These layers, slowly solidifying, formed the earliest landmasses. Unlike the vast continents we recognize today, these were small, scattered islands, fragile yet persistent, floating like islands in a sea of fire. Plate tectonics, though in its infancy, played a vital role in shaping these first continents. As slabs of crust moved, collided, and merged, they created the foundation for mountains, valleys, and the uneven terrain that would define Earth's surface. Each collision was a violent yet necessary act, gradually assembling the pieces of land into larger formations. The minerals released in these processes enriched the soil and created chemical conditions essential for the future emergence of life. Even today, scientists study these ancient rocks to decode the secrets of early Earth, learning how simple geological forces set the stage for everything that followed. The appearance of the first continent was not just a geological event, it was a turning point in the story of our planet. For the first time, there was a solid, enduring place upon which life could eventually arise. Water from the earliest rains began to carve rivers and shallow lakes into these rocky islands. The interaction between mineral-rich rocks and water created a dynamic environment, where chemical reactions laid the foundation for organic molecules, the building blocks of life. Every stream, every mineral vein, and every volcanic deposit played a subtle yet crucial role in transforming a molten world into a habitable one. One of the most fascinating aspects of the first continent was its impermanence. Over millions of years, these land fragments constantly collided, broke apart, and reformed, a cycle that repeated countless times. This ceaseless movement forged a resilient yet flexible crust, capable of withstanding the extreme conditions of early Earth. Mountains were born and eroded, valleys deepened, and plains emerged, all forming the first landscapes that life would one day call home. These proto-continents also influenced Earth's atmosphere. Volcanic eruptions released gases like carbon dioxide and water vapor, contributing to the formation of clouds, precipitation, and eventually weather systems. Even in this early, seemingly hostile world, the first continent acted as a stabilizing force, shaping the climate and environment in ways that allowed the seeds of life to endure. It is remarkable to consider that the very continents we see today, Africa, Asia, Europe, and the Americas, are descendants of these early landmasses. The first continent was tiny compared to what would come later, but it carried within it the potential for every forest, every ocean, and every living being. Its rocky surface, hammered by eruptions and shaped by time, tells a story of persistence, transformation, and resilience. In essence, the first continent was the stage upon which Earth's drama would unfold. It was the silent witness to the birth of oceans, the first spark of life, and the gradual emergence of an environment capable of supporting unimaginable complexity. The first rocks, the first mountains, and the first valleys all carry within them a record of this ancient past, a testament to the patient, relentless forces of nature that transformed a fiery ball of molten rock into a world ready for life. By studying these ancient landmasses today, geologists uncover clues about the formation of continents, the composition of Earth's crust, and the origins of life itself. Every fold in the rock, every trace of mineral alignment, is a window into the distant past. The first continent reminds us that even amidst chaos, stability can emerge. It is a story of beginnings, of fire becoming stone, of islands merging into land, and of a world preparing itself for life that would eventually walk, swim, and fly across it. Billions of years ago, Earth's atmosphere was thick with water vapor and gases released from volcanic eruptions. As the planet cooled, condensation began to occur, and rain fell for the very first time. Picture torrential rains, unending in their intensity, carving basins into the newly formed continents. The mineral-rich water pooled into low-lying areas, forming shallow seas that slowly merged into larger bodies of water. These early oceans were turbulent and hostile, yet they were essential for the chemical reactions that would one day give rise to life. The first oceans were composed of a mixture of water, dissolved minerals, and volcanic chemicals, creating a unique environment. The interaction between water and freshly exposed rocks created the first chemical gradients, which are crucial for prebiotic chemistry, the processes that eventually led to the first organic molecules. These molecules, floating and reacting in the early oceans, laid the groundwork for the origin of life. Geologists today refer to this period as the Archean Eon, a time when the first oceanic crust stabilized. Underneath the surface, volcanic activity continued to shape the seabeds, creating underwater mountains, rifts, and valleys. Hydrothermal vents spewed heat and minerals into the water, providing a rich chemical environment. These vents were likely among the first places where life could have begun, taking advantage of energy sources other than sunlight. Imagine the ocean floor, alive with chemical reactions, slowly nurturing the earliest forms of life that would one day populate the Earth. The formation of the first ocean was also critical for the climate and atmosphere. Oceans act as regulators, absorbing heat and distributing it across the planet. Even in these primordial times, the water began moderating temperature extremes, preventing the planet from becoming entirely inhospitable. These vast water bodies also absorbed carbon dioxide from volcanic eruptions, slowly influencing the composition of the atmosphere and making it more stable for future life forms. One of the most remarkable aspects of the first ocean was its role as a cradle for complexity. The constant movement of water currents, tides, and waves, a mixing of minerals and chemicals, allowing essential compounds to interact. Over millions of years, these interactions produced increasingly complex molecules, some of which formed protective layers, while others began replicating in ways that hinted at the first rudimentary life forms. The ocean was not just a pool of water. It was a dynamic laboratory, setting the stage for the emergence of life. Despite the harsh conditions, the first ocean was vast and enduring. It connected early land masses, allowing chemical and mineral exchange between them. It carved the first shorelines and coastlines, shaping the contours of continents that would later host diverse ecosystems. The ocean's depth, pressure, and chemistry were all in constant flux. Yet this turbulence was precisely what created the ideal conditions for the next chapter in Earth's story life itself. As Earth continued to evolve, the first oceans expanded and stabilized, forming the great basins that would eventually become recognizable seas. These waters witnessed the gradual cooling of the planet, the growth of continents, and the first chemical pathways that made life possible. Every droplet, every wave, and every mineral-laden current carried with it the potential for life, slowly preparing the planet for the explosion of biodiversity that would follow billions of years later. The first ocean was more than just a physical feature. It was a transformative force. It shaped the geology, chemistry, and climate of early Earth, preparing the planet for the emergence of life. Today, when we look at Earth's oceans, we are witnessing the legacy of those first primordial waters, the silent architects of life's beginnings. Without them, continents would have remained barren, and life, as we know it, would never have found a home. In the earliest days of Earth, long before the rise of life or the formation of recognizable continents and oceans, the concept of night was something entirely alien. The planet, still young and volatile, was dominated by fire, molten rock, and a tumultuous sky that constantly glowed with the light of erupting volcanoes and the faint shine of a cooling surface. Yet, slowly, as the planet's surface began to stabilize, the first true night emerged, a moment when darkness fell upon the newly forming Earth, bringing with it profound change. The first night was unlike anything modern humans experience today. Without a stable atmosphere or a familiar sky, darkness was not merely the absence of sunlight. It was an unfamiliar and overwhelming force. As the early Earth rotated on its axis for the first time, portions of the planet would drift away from the young sun, plunging the rocky, molten surface into shadow. This rotation, simple as it seems now, was crucial. It introduced the very concept of day and night, marking the passage of time in a rhythm that would become essential for the evolution of life. During this early night, temperatures dropped drastically on the surface. The cooling of the crust allowed water vapor to condense, feeding the first nascent oceans and rivers. Shadows fell over newly formed mountains and valleys, revealing a landscape of contrasts. Glowing lava streams still carved their paths through darkness, while cooled stone formed stable landmasses beneath a sky devoid of stars as we know them. In these intervals of darkness, the Earth's surface experienced its first cycles of thermal fluctuation, setting the stage for chemical interactions that were vital for prebiotic chemistry. The first night also influenced atmospheric conditions in profound ways. As darkness prevailed, gases trapped in the young atmosphere began to settle and interact differently than during the heated day. Carbon dioxide, nitrogen, and water vapor behaved in a complex ballet, contributing to weather phenomena such as primitive storms, lightning, and condensation. These nocturnal processes played a significant role in shaping the earliest climate systems and creating microenvironments where life could eventually gain a foothold. Remarkably, the first night revealed the dynamic interaction between Earth's geological activity and the emergent cycle of darkness. Volcanoes continued to erupt, spewing incandescent lava into the darkened sky, while tectonic movements subtly reshaped continents and shorelines in silhouette against glowing magma. Lightning, a frequent visitor during early storms, illuminated these landscapes briefly, creating the first natural nighttime spectacles. This interplay of light and darkness not only sculpted the physical terrain, but also facilitated chemical reactions in water bodies and mineral surfaces, providing energy sources for early organic synthesis. Furthermore, the absence of sunlight during these first nights allowed temperatures to fall sufficiently to influence the early ocean's chemistry. The cooling effect promoted the precipitation of minerals, forming rocky seabeds rich with the compounds necessary for early life. It was during these dark hours that the planet's surface began to accumulate stable chemical gradients, variations in temperature, mineral concentration, and acidity that were crucial for the development of complex molecules. Every shadowed hour contributed incrementally to the preparation of the planet as a cradle for life. The concept of night also introduced the idea of temporal cycles. Even though life had not yet emerged, the alternating phases of light and darkness influenced tidal interactions, volcanic cooling patterns, and the gradual stabilization of atmospheric pressure. The first night, therefore, was not merely a period of darkness, but an active participant in shaping the environmental conditions that would later allow organisms to regulate biological clocks, navigate habitats, and evolve circadian rhythms. Astronomical factors also began to influence these early nights. While the moon had not yet fully formed or stabilized in its orbit, its gravitational pull started affecting tides and subtly influencing the early ocean's circulation patterns. These interactions between gravity, the rotational period, and the emerging light-dark cycle created a dynamic planetary rhythm, precursor to the environmental cycles that would govern life once it appeared. As eons passed, the first nights gradually became more familiar in concept, even if the conditions remained extreme by modern standards. Dark periods allowed cooling, mineral deposition, and chemical reactions to occur in ways that the constant heat of the day could not permit. The first night represented the planet's capacity for balance, a time when chaos gave way to structure, when light and heat yielded to shadow and cold, and when the stage was being set for biological processes that would thrive in cycles of day and night. The first night, though devoid of human observation or consciousness, was one of the most transformative events in Earth's early history. It shaped temperatures, influenced atmospheric behavior, and prepared the oceans and continents for the eventual emergence of life. In essence, the first night was the planet's silent architect, working invisibly yet fundamentally to create the conditions for all that would follow. As the young Earth completed its initial rotations, a new phenomenon began to emerge: the first morning. Unlike the mornings we know today, with soft golden light spilling across familiar landscapes, this first morning was raw, powerful, and transformative. It marked the transition from the deep darkness of the first night to the arrival of sunlight on a planet still in its infancy, a moment when the energy of the young sun first touched solid land and liquid water in a rhythm that would eventually define time itself. The first morning was a result of the Earth rotating steadily on its axis, exposing portions of the surface to the intense radiation of the sun. Before this, light had flickered in bursts from volcanic eruptions and molten lava flows. But now, a consistent and directional light source began illuminating the newly formed continents and oceans. Imagine a landscape where molten rocks glowed under sudden sunlight, mineral-rich pools reflected the nascent rays, and shadows stretched across jagged terrains for the very first time. This was a world awakening, its surfaces reacting chemically, physically, and thermodynamically to a light that had never before reached it in such a manner. The first rays of sunlight triggered profound changes in the Earth's environment. The warmth from the sun accelerated the evaporation of water from the shallow seas, contributing to the formation of early clouds and precipitation cycles. Atmospheric currents began to stabilize under the influence of solar radiation, initiating primitive weather patterns. Even the rocky surfaces of the first continents responded. Thermal expansion and contraction shaped cracks, fissures, and valleys, gradually sculpting the landscape into forms that would guide rivers and the earliest bodies of water. On a chemical level, the first morning provided energy for reactions that could not occur in darkness. Photochemical reactions, the breaking and reforming of molecules under light, started shaping the primordial chemistry of the planet. Sunlight, interacting with water and atmospheric gases, contributed to the synthesis of simple organic molecules, the precursors of life. In essence, the first morning was the catalyst for chemical innovation, allowing nature to explore possibilities that darkness alone could not facilitate. The first morning also influenced temperature gradients across the planet. Areas exposed to sunlight began to warm, while regions still in shadow remained cool. These variations created convection currents in both the atmosphere and oceans, promoting the mixing of minerals, gases, and water. Such dynamic systems were essential for preparing habitable niches, eventually allowing microorganisms to thrive in environments that were gradually becoming more complex and stable. Volcanic landscapes, once glowing with molten eruptions during the night, now interacted differently with sunlight. The heat from lava combined with solar energy accelerated mineral weathering, producing sediment and nutrients that would eventually nourish the first living systems. Tidal interactions with the forming moon subtly influenced the first morning cycles, shaping coastlines and ocean basins in ways that would become permanent features of the planet's geography. This first morning was also a time of dramatic contrasts. Shadows stretched across mountains, valleys, and volcanic plains, while sudden flares of light illuminated mineral-rich waters, revealing patterns of color and texture never before seen on Earth. The interplay of light and shadow sculpted the planet in real time, creating the first impressions of landscapes that life would one day inhabit. Each ray of sunlight, striking different surfaces, initiated processes of erosion, crystallization, and chemical change, reinforcing the dynamic relationship between light, heat, and matter. From a geological perspective, the first morning was essential for the stabilization of the planet's crust. The cyclical heating and cooling induced by day and night caused stress and tension in rock layers, leading to the slow formation of mountain ranges and valleys. Sunlight, though seemingly simple, became a fundamental agent in shaping the physical contours of Earth, preparing the stage for rivers, lakes, and eventually ecosystems. The first morning also set in motion long-term cycles of energy transfer. Sunlight absorbed by water and land was redistributed via winds, currents, and tidal flows, forming the earliest patterns of climate regulation. Over millions of years, These interactions would define temperate zones, ocean currents, and seasonal shifts. Without the first morning, Earth would have remained a stagnant, molten, and uninhabitable sphere, unable to support the delicate balances required for life to flourish. In essence, the first morning was the planet's awakening. It brought light, warmth, and energy to a world still learning to stabilize itself. It transformed darkness into a rhythm of day and night, creating a template for chemical, geological, and eventually biological cycles. Each ray of the young sun played a part in orchestrating the delicate balance of conditions that would make life possible. The first morning was not just a moment of light, but the beginning of Earth's daily heartbeater rhythm that has persisted for billions of years, carrying the story of our planet from its fiery infancy to the thriving world we inhabit today. First winter in the early eons of Earth, long before life adorned the continents or oceans, the planet experienced its first true winter. Unlike the winters we know today, marked by snow-covered landscapes and rhythmic seasonal changes, the first winter was a period of extreme contrasts, a testament to the planet's volatile and dynamic nature. It was a time when the young Earth, still cooling from its molten birth, faced dramatic temperature drops, revealing the raw power of climate and the fragile balance that would eventually sustain life. The first winter occurred as Earth's rotation and axial tilt began to stabilize, creating variations in sunlight exposure across different regions. While some areas basked in prolonged light, others plunged into extended darkness. These cycles introduced the concept of seasonal temperature fluctuations for the very first time. The cooling effect during these extended dark periods was extreme. Shallow seas partially froze in certain regions, and newly formed rock surfaces contracted, forming fissures, cracks, and ice-laden valleys. This harsh environment was simultaneously destructive and creative, reshaping the landscape in ways that would influence the evolution of the planet. Temperature gradients during the first winter had profound geological and chemical implications. Cooling surfaces caused volcanic flows to solidify rapidly, creating layered rock formations. Simultaneously, ice formation in ocean basins and shallow pools concentrated minerals and salts, leading to chemical environments that facilitated prebiotic reactions. These interactions were essential in producing organic molecules, which, over millions of years, would become the building blocks of life. In essence, winter became not just a season of cold, but a catalyst for Earth's chemical and geological evolution. The first winter also significantly affected atmospheric circulation. As regions cooled, dense, cold air masses began to move toward warmer areas, creating primitive wind systems and weather patterns. These early winds interacted with the planet's oceans, generating currents that redistributed heat and minerals. In this way, the first winter played a critical role in regulating the young planet's energy balance, shaping environments that would later become habitable. Volcanic activity, though reduced in some areas due to cooling, remained a defining factor during the first winter. Eruptions injected ash and gases into the atmosphere, interacting with the cold air to create primitive storms, lightning, and precipitation. Snow and ice began to accumulate in high-altitude regions and polar basins, setting the stage for Earth's first glacial formations. These early ice caps, though temporary in scale, were crucial in sculpting the planet's surface, carving valleys and plains, and influencing the flow of rivers and the formation of lakes. The first winter also introduced dynamic interactions between land, water, and air. As ice formed, it reflected sunlight, influencing regional temperatures and contributing to feedback loops that further regulated the climate. Seasonal freezing and thawing caused erosion and sediment transport, gradually redistributing minerals across the continents and ocean basins. These processes enriched the young Earth with diverse chemical compositions, essential for the later emergence of complex ecosystems. Marine environments experienced dramatic changes during the first winter. Ice formation in shallow seas concentrated salts and minerals, producing unique chemical conditions. Hydrothermal vents under frozen surfaces continued to release heat and nutrients, creating localized zones where temperature and chemical gradients supported complex reactions. These zones likely became early laboratories for the synthesis of organic compounds, demonstrating that even the harshest conditions could foster the precursors of life. The concept of the first winter also affected energy distribution across the planet. Cold regions acted as reservoirs, absorbing and storing energy from sunlight during the brief, warm periods. This energy redistribution stabilized early weather systems, contributing to the emergence of climatic patterns that would persist for millions of years. In essence, winter established a rhythm, a balance between extremes, that the planet relied upon for stability and continuity. Beyond its immediate effects on geology and chemistry, the first winter demonstrated Earth's capacity for resilience. Despite extreme cold, volcanic activity, and chemical turbulence, the planet continued to evolve, preparing environments that could eventually support life. The first winter was not merely a season. It was a transformative event, shaping landscapes, regulating climate, and creating the conditions necessary for oceans, continents, and, ultimately, living organisms to thrive. In summary, the first winter was a profound chapter in Earth's early history. It brought cold, darkness, and extremes, yet it catalyzed geological, chemical, and atmospheric processes that shaped the planet's surface and environment. Every frozen pool, every ice-laden valley, and every temperature gradient contributed to a delicate balance that would make life possible. It was a season of transformation, a reminder that even in harshness, creation and preparation were at work on the young Earth. The first sunlight to touch the surface of Earth was more than a simple illumination. It was a transformative force that reshaped the young planet in profound ways. Unlike the gentle morning light we experience today, the first rays of the sun were raw, intense, and direct, striking a world that had yet to develop the protective layers of atmosphere and ozone. The energy carried by these photons initiated chemical reactions, influenced geological processes, and subtly regulated the environment in ways that would set the stage for the emergence of life. During these early moments, sunlight penetrated thin, volatile clouds and reached the molten and rocky surface of continents and oceans. The energy was absorbed differently depending on the terrain. Dark, volcanic rocks heated quickly, causing expansion and thermal stress, while reflective mineral-rich waters absorbed light more gradually, contributing to evaporation and cloud formation. These early interactions between light and surface created micro-environments of temperature variation, which in turn facilitated chemical diversity, a crucial factor for the synthesis of complex organic molecules. Sunlight also played a key role in atmospheric evolution. Ultraviolet radiation, though harmful by today's standards, contributed to the breakdown of simple gases. producing reactive compounds that would participate in early chemical cycles. Water vapor, carbon dioxide, and other volcanic gases interacted under sunlight to form a primitive photochemical network, influencing early climate and weather patterns. These reactions were fundamental in shaping the chemistry of the oceans, rivers, and shallow pools that would later serve as cradles of life. The first sunlight had a direct impact on the oceans as well. Shallow waters warmed under solar radiation, creating thermal gradients that drove currents and mixing processes. This circulation distributed minerals, nutrients, and dissolved gases throughout the young oceans, enhancing chemical interactions essential for the formation of prebiotic molecules. Hydrothermal vent regions, already chemically active, now experienced additional energy input from sunlight, allowing more complex reactions to occur and increasing the likelihood of molecular self-organization. On land, sunlight induced changes in the crust as well. Repeated heating and cooling cycles expanded fissures, created new cracks, and reshaped landscapes. This not only prepared the terrain for future water flow, but also influenced the distribution of minerals essential for life. The first sunlight, striking these raw surfaces, effectively sculpted the planet, guiding erosion patterns, sediment deposition, and the early formation of valleys, plains, and riverbeds. One of the most critical roles of the first sunlight was its influence on energy cycles. By delivering consistent energy during the early morning hours, sunlight drove evaporation, cloud formation, and precipitation patterns that stabilized the young planet's climate. These processes established the first dynamic interactions between land, water, and air, forming a feedback system that would persist and become more complex over billions of years. Moreover, sunlight was a silent driver of chemical complexity. Photons energized molecules in ways that thermal energy alone could not. Reactions that split water, combined minerals, or created reactive radicals were all catalyzed by sunlight in the shallow pools along early shorelines. This energy allowed the first steps toward the interplay between sunlight, water, and minerals, created the conditions necessary for the emergence of self-replicating molecules. As days turned into cycles, the first sunlight established a rhythm that influenced tidal interactions, rotational stability, and the early organization of planetary weather systems. Regions facing the young sun experienced heating, while areas in shadow cooled, producing gradients that would later guide ocean currents, wind patterns, and seasonal variations. This interplay between light and dark, heat and cold, laid the groundwork for the first predictable environmental cycles on Earth. In essence, the first sunlight was not merely an illumination. It was a catalyst for geological, chemical, and environmental transformation. It activated the planet's surface, energized its oceans, and orchestrated a subtle balance between energy input and environmental response. Without this first exposure to solar energy, the intricate dance of molecules, minerals, and water that eventually led to life could not have taken place. The first sunlight represents a moment of awakening, a time when the young planet, forged from chaos, received the energy necessary to drive change, sustain chemical reactions, and regulate its evolving climate. Every ray, every photon, contributed to shaping the Earth's physical and chemical landscape, ensuring that the planet would eventually become not only stable, but capable of supporting life. In every sense, the arrival of sunlight marked the beginning of an era in which Earth could progress from a molten, chaotic world to a vibrant, dynamic planet teeming with possibility. Color of sky. The earliest Earth existed under a sky unlike anything seen today. The first atmosphere, thick with gases released from volcanic activity and primordial outgassing, created a canopy that refracted and filtered sunlight in unusual ways. The concept of sky color was not yet as humans perceive it. It was a dynamic palette shaped by chemical composition, particle density, and the scattering of light. The first sky was a vivid interplay of tones, smoky grays, muted reds, and faint blues, constantly shifting as the planet's atmosphere evolved. During this period, Earth's atmosphere was dominated by water vapor, carbon dioxide, nitrogen, and traces of other volcanic gases. Dust and ash particles from frequent eruptions filled the sky, scattering sunlight unevenly and creating diffuse, glowing bands of color across the horizon. At times, the sky would appear blood red during heavy volcanic activity, as sunlight filtered through thick clouds of ash and chemical aerosols. At other moments, the sky displayed hints of blue as lighter gases allowed selective scattering of shorter wavelengths of light, though this was faint and fleeting compared to the brilliant blues we observe today. The scattering of sunlight by atmospheric particles, what we now call Rayleigh scattering, was already at work in primitive form. Sunlight striking suspended ash, dust, and gas molecules created gradients of color across the sky, often producing stark contrasts between horizon and zenith. The interaction of light with water vapor in nascent clouds produced hazy effects, lending the early sky a luminescent quality. These phenomena were essential, not merely aesthetic, as they affected the thermal balance of the planet, directing energy absorption and influencing surface temperatures. The color of the sky was also closely linked to Earth's weather patterns. Clouds composed of condensed water vapor reflected sunlight during the day, diffusing light across vast stretches of atmosphere and casting subtle shadows on the rocky terrain below. Early storms generated dramatic contrasts in sky color. Lightning illuminated dense, smoky clouds, producing sudden flashes of white and silver against a background of muted reds and purples. These dramatic visual effects were indicators of the planet's dynamic meteorology and foreshadowed the complex climate systems that would evolve over billions of years. Chemical reactions in the atmosphere also played a critical role in shaping sky color. Ultraviolet sunlight interacted with gases, initiating photochemical processes that broke down molecules and created reactive compounds. These reactions contributed to subtle changes in the composition of the atmosphere, affecting light scattering and absorption. The early sky, therefore, was not only a visual spectacle, but also a chemical laboratory, where sunlight, gases, and particles interacted to shape the planet's evolving environment. On a daily basis, the rotation of the planet introduced variability in sky color. During the first morning and subsequent daytime periods, sunlight penetrated the atmosphere at different angles, producing a range of hues across the horizon. As the young Earth rotated, regions in shadow would experience a muted, grayish palette, while regions facing the sun revealed brighter and warmer tones. This continuous variation in sky color influenced the early thermal cycles, contributing to the development of temperature gradients that would later stabilize weather and ocean currents. The early sky also indirectly influenced the oceans. Scattering of sunlight across the atmosphere affected the heating of shallow waters, creating gradients of temperature and mineral distribution. These gradients drove the first currents and mixing patterns. which were essential for distributing nutrients and sustaining chemical reactions crucial for the emergence of life. Even the faint hint of blue in the early sky played a role in moderating the energy absorbed by the oceans, highlighting the interconnectedness of atmospheric color and planetary processes. As volcanic activity continued, the sky occasionally shifted dramatically. Massive eruptions released plumes of ash and gases that temporarily darkened the horizon, producing spectacular red, orange, and violet sunsets and sunrises. These events, though transient, had lasting effects on surface temperatures and the chemical composition of the atmosphere. Over time, the continuous interplay between sunlight, gases, and particles gradually stabilized the sky's appearance, laying the foundation for the more familiar shades of blue and white that would dominate Earth's atmosphere millions of years later. In essence, the first sky was a constantly evolving canvas shaped by the composition of gases, volcanic activity, scattered light, and early weather phenomena. Its colors were a reflection of the young planet's volatility and dynamism, influencing temperature, chemical reactions, and the physical shaping of continents and oceans. Observing the first sky was witnessing the Earth in its formative years, where every color, shade, and glow carried the story of a planet in motion, preparing to host the complexity of life. First temperature, the young Earth, freshly formed from the coalescence of cosmic dust, molten rock, and volatile gases, experienced its first real temperature fluctuations in ways that would shape the trajectory of the planet for billions of years. Unlike the stable climates familiar to life today, the first temperature was highly dynamic and unpredictable, governed by a combination of solar radiation, volcanic activity, atmospheric composition, and the slow cooling of the planet's interior. The extremes of heat and cold defined the surface, oceans, and atmosphere, setting the foundation for Earth's geological and chemical evolution. Initially, the planet's surface was dominated by residual heat from formation processes. Molten lava covered vast regions, radiating intense heat into the early atmosphere. Temperatures varied widely depending on location. Volcanic plains could exceed thousands of degrees Celsius, while shadowed basins and polar regions were slightly cooler, yet still far hotter than present-day Earth. This extreme heat influenced mineral crystallization, the formation of early rock layers, and the stabilization of continental crust. Every temperature variation played a critical role in determining where oceans could form, where minerals would accumulate, and how gases would circulate in the atmosphere. The interaction between sunlight and the surface added a new layer of complexity. As the first rays of the sun touched the planet, they warmed areas exposed to direct radiation, while regions in shadow remained comparatively cooler. These temperature gradients created convection currents in both the atmosphere and the oceans, driving the initial patterns of weather and chemical mixing. Shallow pools of water warmed unevenly, establishing thermal layers that promoted chemical reactions essential for prebiotic chemistry. Temperature, therefore, became not merely a measure of heat, but a driving force for chemical diversity. Volcanic activity contributed further to the first temperature variations. Eruptions released not only molten lava, but also vast quantities of gases, including carbon dioxide, sulfur dioxide, and water vapor, which influenced atmospheric opacity and heat retention. Dense clouds of volcanic ash temporarily reflected sunlight, causing cooling in some regions, while the heat from lava flows and geothermal activity continued to raise temperatures locally. These contrasts between hot and cold zones created complex microenvironments that shaped the early landscape and influenced the distribution of chemical compounds across the planet. The oceans responded sensitively to these first temperature changes. Warm regions promoted evaporation, leading to the condensation of water vapor and the formation of early clouds. Cooler regions retained denser water, generating currents and mixing patterns that redistributed heat and minerals. Temperature fluctuations also influenced the formation of ice in certain high-altitude or polar basins, while simultaneously allowing liquid water to exist elsewhere. This delicate balance of heat and cold established the first dynamic environmental cycles, laying the groundwork for life-supporting ecosystems millions of years later. Atmospheric temperatures were equally variable. Dense early clouds trapped heat near the surface while also reflecting solar energy, creating pockets of warmth and cold that moved dynamically with wind patterns. The first temperature cycles affected chemical reactivity in the atmosphere. Cooler zones allowed condensation of water and deposition of minerals, while warmer zones accelerated photochemical reactions driven by sunlight. Temperature, in effect, acted as a regulator of both physical and chemical processes, determining where and how different reactions could occur. The first temperature also interacted with the rotational period of the planet. As Earth rotated, regions alternated between light and dark, hot and cold, producing primitive diurnal cycles. These cycles were the initial framework for predictable environmental rhythms, which would later influence circadian patterns in living organisms. Even before life emerged, temperature was already dictating patterns of energy flow, chemical interaction, and physical change, demonstrating its fundamental role in planetary evolution. Over time, the interplay between heat from the interior, solar radiation, and atmospheric composition began to stabilize regions of the planet. Thermal gradients became more predictable. Volcanic activity became intermittent rather than constant, and the oceans developed more coherent circulation patterns. These changes allowed for the accumulation of minerals and the formation of environments suitable for the chemical precursors of life. Temperature, therefore, was not only a measure of energy, but a critical agent of transformation. In conclusion, the first temperature on Earth was a complex, dynamic phenomenon that shaped the young planet in multiple dimensions. It influenced the cooling and solidification of the crust, the formation and mixing of oceans, the chemical reactivity of the atmosphere, and the eventual emergence of stable environmental cycles. The extremes of heat and cold, combined with the variability introduced by sunlight, rotation, and volcanic activity, created the conditions necessary for the development of life. The first temperature was the planet's invisible architect, working tirelessly to prepare Earth for the wonders that were yet to come. First atmosphere. The first atmosphere of Earth was unlike the one we breathe today. It was a dynamic, volatile envelope of gases, constantly changing in composition, density, and temperature. Formed shortly after the planet coalesced from cosmic dust and molten rock, the early atmosphere was the product of volcanic outgassing, cometary impacts, and the gradual accumulation of lighter gases from the solar nebula. This initial layer of air was both a protective shield and a chemical laboratory, setting the stage for weather systems, temperature regulation, and ultimately, the emergence of life. During this early period, the atmosphere consisted primarily of water vapor, carbon dioxide, nitrogen, methane, and traces of ammonia and other reactive gases. Free oxygen was virtually absent, making it a reducing environment. Volcanic eruptions continually injected sulfur dioxide, hydrogen, and carbon monoxide, creating localized pockets of dense, toxic air. Thick clouds of steam and volcanic particulates shrouded the young planet, scattering sunlight in diffuse patterns that influenced the temperature and chemistry of the surface. The first atmosphere was both nurturing and hostile, providing essential ingredients for life while simultaneously presenting challenges for stability. The dynamic nature of the early atmosphere influenced surface conditions profoundly. Thermal gradients formed between sunlit regions and shadowed zones, driving primitive wind patterns and convection currents. These movements helped redistribute heat and moisture, contributing to the early formation of clouds and precipitation. Rainfall, though sporadic, acted as a natural mechanism for erosion, shaping the surface and transporting minerals to oceans, lakes, and basins. Atmospheric pressure, unevenly distributed across the young planet, played a critical role in determining where water could accumulate, freeze, or evaporate, effectively sculpting the first habitable environments. The interaction between sunlight and the first atmosphere was a defining feature of early Earth. Ultraviolet radiation broke down simple molecules in the air, producing reactive compounds that participated in the formation of organic molecules in surface waters. The scattering of light by clouds, gases, and volcanic ash created shifting sky colors and affected thermal patterns across the continents and oceans. In essence, the first atmosphere was a mediator, transforming solar energy into chemical and physical processes that would drive planetary evolution. Water vapor, the dominant gas in the early atmosphere, played a dual role. It acted as a greenhouse gas, trapping heat near the surface, while also participating in the formation of clouds and precipitation. Condensation in the upper atmosphere produced primitive storms, lightning, and rain, which contributed to the erosion of rocks and the cycling of minerals. This continuous interplay between air, water, and sunlight created a dynamic feedback system, crucial for regulating temperature, distributing nutrients, and preparing the planet for the emergence of living systems. The chemical composition of the first atmosphere also set the stage for the formation of the ozone layer. Although in a very rudimentary form, reactive compounds generated by photochemical reactions began to absorb some ultraviolet radiation, protecting the surface from excessive solar energy. This process, though slow, would eventually stabilize the environment, allowing more complex chemical and biological processes to occur. The first atmosphere, therefore, was both a protective blanket and a reactive engine, mediating interactions between the sun, the surface, and the oceans. Volcanic activity remained a constant driver of atmospheric dynamics. Gases released during eruptions created localized pressure changes, altered the distribution of heat, and influenced chemical reactions in the air. Ash particles scattered sunlight, creating transient cooling effects, while also contributing to the scattering of light that shaped early sky colors. These eruptions injected essential minerals into the atmosphere, which then settled into oceans and soil, enriching the environment with the raw materials necessary for prebiotic chemistry. Over time, the first atmosphere evolved, gradually stabilizing as volcanic activity decreased and gases redistributed through winds, rainfall, and chemical reactions, although still vastly different from today's breathable air. This initial envelope of gases provided the foundation for the development of more complex atmospheres, the regulation of climate, and the protection of emerging biological systems. The first atmosphere was, in essence, the planet's life support framework before life itself existed, dynamic, reactive, and essential precursor to Earth's habitability. First air. The first air on Earth was a phenomenon of transformation, marking the transition from a world dominated by molten rock, steam, and volcanic gases to a planet with a dynamic, circulating atmosphere. This initial breath of wind, carried by the early rotation of the Earth and shaped by the planet's uneven heating, was not simply motion of gases. It was the first agent of change, distributing heat, moisture, and chemical compounds across the surface in ways that would forever alter the trajectory of planetary evolution. The early atmosphere consisted primarily of water vapor, carbon dioxide, nitrogen, methane, and traces of ammonia, sulfur dioxide, and hydrogen. Oxygen was virtually absent, making it a reducing environment that allowed for complex chemical reactions without immediate oxidation. The first movements of air were driven by temperature gradients created by the young sun's uneven heating of the planet's surface. Hot, volcanic plains radiated energy into the atmosphere, causing nearby gases to rise, while cooler shadowed regions drew denser air downward. These early convection currents were the seeds of wind, the first tangible movement of the atmosphere that would shape weather, erosion, and the distribution of minerals and heat. As the first air moved, it interacted with other components of the environment. Dust and ash from volcanic eruptions became suspended in the circulating gases, scattering light and contributing to the formation of early clouds. Water vapor, transported by winds, condensed into rain, initiating the first precipitation cycles. This rainfall began the slow but persistent reshaping of landscapes, eroding rock formations, transporting minerals, and carving primitive river channels. Air, for the first time, became a dynamic sculptor of the planet's surface. Chemical reactions in the first air were equally transformative. Sunlight interacting with gases in the atmosphere initiated photochemical reactions that produced reactive molecules, including formaldehyde, hydrogen cyanide, and other organic precursors. These molecules were carried by the winds to shallow pools, volcanic basins, and ocean margins, where they participated in the earliest steps toward prebiotic chemistry. The movement of air, therefore, was not merely physical, but chemical, distributing essential building blocks for life across the planet. Temperature variations driven by solar exposure further enhanced air circulation. Regions facing the young sun warmed rapidly, causing air to rise and create low-pressure zones, while shaded areas remained cooler, generating high-pressure zones. This difference produced wind systems that transported heat from hot regions to cooler ones, beginning the first cycles of thermal balance that would stabilize climate over geological time. The first air acted as a global energy distributor, transferring the sun's energy from region to region, preparing the planet for more complex weather systems. Volcanic activity continued to contribute to the properties of the first air. Explosive eruptions released immense amounts of gas and particulate matter, temporarily altering local wind patterns and chemical composition. Ash clouds reflected sunlight, creating cooling effects and influencing temperature gradients, while gases such as sulfur dioxide and methane contributed to chemical interactions in the atmosphere. These dynamics reinforced the first air's role as both a physical and chemical agent, shaping the Earth's environment on multiple scales simultaneously. The interaction between the first air and oceans was crucial. Winds facilitated the movement of surface waters, generating currents that mixed minerals, heat, and dissolved gases. Evaporation driven by sunlight and carried by winds contributed to humidity cycles and early cloud formation, further enhancing precipitation and the redistribution of water across the planet. In this way, the first air linked the atmosphere and oceans, creating a feedback loop essential for stabilizing temperature, distributing nutrients, and preparing habitats for the first living systems. Over time, the first air became increasingly organized, developing recognizable patterns of circulation. Convection currents, influenced by rotation, temperature, and surface features, established early climate zones. These patterns allowed for more predictable cycles of heat, moisture, and chemical distribution. While still vastly different from today's winds and atmospheric behavior, the first air represented the planet's initial attempt at equilibrium, balancing the energy of the sun with the thermal and chemical properties of Earth's surface and oceans. In essence, the first air was a transformative force, moving across a young and chaotic planet to distribute energy, moisture, and chemical compounds. It sculpted landscapes, regulated temperature, facilitated chemical synthesis, and prepared the stage for the emergence of life. The motion of these early gases, driven by sunlight, volcanism, and planetary rotation, marked the beginning of dynamic processes that continue to govern Earth's atmosphere today. Every gust, every swirl of first air carried the potential for change, shaping a planet that was learning to breathe, to circulate, and to sustain the intricate balance necessary for life. Disclaimer section. Thank you for joining us on this journey through the origins of our planet, from the first continent and ocean to the earliest air and sunlight. We hope this documentary has given you a deeper understanding of Earth's formative processes and the extraordinary forces that shaped the world we inhabit today. This video is a product of careful research and synthesis from scientific studies, including findings from geological surveys, atmospheric modeling, and astrophysical observations. While we have based the content on reliable sources, some aspects of early Earth remain theoretical and reconstructed from current evidence. The story presented here combines scientific understanding with documentary storytelling to provide a comprehensive and engaging overview. If you found this video informative and inspiring, make sure to like, subscribe, and share it with anyone curious about the mysteries of our planet. Leave a comment telling us where you are watching from and what fascinated you the most about Earth's first moments. Your engagement helps us bring more detailed and research-based documentaries to life. Remember, this content is educational and intended to inform viewers about Earth's early history. Some depictions are illustrative reconstructions based on current scientific models and should be viewed as such. For deeper exploration, refer to sources from planetary science, geology, and atmospheric chemistry.